Okay, so in today's class, what we're going to cover is we're going to go over a few more. Basically, we're going to cover balances again, but we're going to use balances as a way to derive and manipulate thermo functions. So the balances are going to be sort of arbitrarily constructed systems, but you'll see why these particular systems are useful for deriving like the Helmholtz and the Gibbs for energy. Okay, so first let's do a quick recap of writing down the different ways of energy balances. So if we write out, first of all, what color do we have? What's the easiest color? Is white the best color? Is the red hard to see?
Green is probably, because the human eye can see green easier, I believe.
Yeah, green's a zany color though to use. I'll stick with white, but I'll use green as the secondary. I like that one. Okay, so if we write out the general energy balance for an arbitrary open system, right, this is going to be our starting point for most of what we're going to cover in the first like 2 weeks or so. Well, this and the entropy balance equation, but for an open system. So I want to go over a couple of different ways that we can write this differently, because sometimes this isn't going to be the best equation to use to solve things. So if it's closed, what is the simplification that we can use? M dot I is equal to 0, in which case we have du dt is equal to q dot plus w dot. So any heat that goes into the system has to go into work somehow. The total energy of the system, the total energy system can grow if it's not steady state. So then what we typically will say then is oftentimes this is the differential form of the energy balance equation. Right, we're looking at a differential unit of time, trying to keep track what is the rate of change of the energy of the system. Oftentimes, though, it'll be easier to look at what is the total amount that has changed over a period of time, in which case we'll use what they call the integral form. So if you do over a period of time, so over some delta t period, we can integrate du dt. Now, again, thermomath is a little bit fast and loose. Oftentimes, we'll just jump straight ahead and say, okay, well, that's u of state 2 minus u of state 1. Right? We've magically integrated the function. We're just saying, oh, that's delta u. That's all we're going to bother with. Then if we integrate the right-hand side of the equation, we just get rid of the dots. It's the total Q that has entered the system plus the total W. In this case, recall that the delta is just final minus initial. And in this case here, this is as a result of time but I'm going to go over right now another circumstance where we use the delta, where the delta is a little bit different meaning. Okay, so a lot of times we'll just do this. We'll just integrate du and then boom, it's automatically delta t, or I'll integrate dh and it's automatically delta h. Now if we go to an open and steady state system, du dt is equal to what always?
0.
0. It's steady state. Everything dt goes away. Always goes away in a steady state system. In which case we have summation of m dot h hat. I can put the i's in here, plus q dot plus w dot. So if we simplify this system down here to say that there's only one stream in and one stream out of the system, we can have Q, we can have W. Right, so if we write the system like this, we can then further simplify our general energy balance equation. In which case we have 0 is equal to the mass flow rate times by the enthalpy out minus the enthalpy in. plus rate of Q plus rate of W. And again, as a reminder, the hat in this case is joules per kilogram. So that everything we're adding up is going to be in terms of power, because this is a differential form. So the work is going to be joules per unit time. So in this case, if we have a mass flow rate of kilograms per second, everything should work out to be what is the rate of energy going into or out of the system. In this case, the overall rate is 0 because it's steady state. But we notice we have dimensional homogeneity here, right? Because du is joules, dt is seconds, right? So everything is adding up quite nicely in terms of the units. So if we rearrange this expression here, we can get it into a form where we have m dot h hat. Oh, I'm sorry, I messed this up. This should be, I jumped ahead. This should be h hat in, this should be h hat out. Right, at this stage, at least for this equation here, right, we're just tallying up what's going in and what's going out of the system. I jumped ahead a little bit. But if we move it to the other side of the equation, then we get h hat out minus h hat in, which we can write as m dot times delta h, which is equal to q dot plus w dot. But in this case here, the delta h is out minus in, as opposed to final minus initial. But you can kind of see how they're loosely related, but technically it's quite a bit different. Now, this isn't necessarily something that I'll see a lot of people having an issue with, but especially in undergraduate classes, this is something that people always jump to the, Q is equal to delta H, but it's important to notice the distinction between sort of a delta in terms of the integral form when you're going from state 1 to state 2 versus a delta when you're talking about an open system balance. So this unique circumstance here where you can have the delta H is really just when you have a simple system of one stream in and one stream out. Most of what we'll be dealing with, though, is related back sort of this integral form here. We're not necessarily going to be calculating a lot of delta U's from state 1 to state 2, but we're mostly going to be focused on calculating delta H's from state 1 to state 2. So when we talk about fluid phase equilibrium, what we're really curious to know is, or we're talking about sort of state changes, is how much energy does it take to go from one state at temperature pressure to another state at temperature pressure. But that's a little bit different than when we're talking about an open and steady state system here, where we have a delta H of this form. And the same thing holds true for entropy balances as well. Okay, so this is something I'd just like to go over just as a refresher to make sure that everyone's on the same page with how we write this. So if we have a more complex system, let's say we're doing an energy balance on a flash separator or a distillation column. Right? You've got one fluid stream in, and then you've got two fluid streams out, potentially at two different phases. There's no way that you can conveniently write a delta H. And in that case, you'll have to keep the form more complex and just keep track of all of the enthalpies in and all the enthalpies out. So very rarely will we be able to simplify our expressions to a simple Q is equal to delta H or W is equal to delta H. Okay, so now let's talk about deriving the Helmholtz and Gibbs energy. So first we'll start off with the Helmholtz. So we're going to draw an arbitrary system. And in this case here, we're going to have a Q term in. We're going to have a W term in. The temperature is going to be constant. And the volume is going to be constant. So another way that I could state this is I could say that it's going to be a rigid-walled system. So oftentimes, the Helmholtz energy is called the closed. So it's closed, meaning no mass in, no mass out, isothermal, constant volume. Or in terms of sort of stat mech speak, we would call this the NVT ensemble. That's how we're performing our calculations. So if you ever look at the literature on thermodynamic calculations for, let's say, polymers or liquid mixtures. Oftentimes they'll not bother with the Gibbs energy, they'll just bother with the Helmholtz energy, because typically the liquid phase is going to be approximated as incompressible. So if you ever look at sort of phase equilibrium studies, if it involves phase equilibrium with the liquid phase, it's almost always delta A as opposed to delta G, what chemical engineers are most used to. Because with vapor-liquid equilibrium, you really do care about the pressure because the pressure significantly impacts the properties of gases. But for liquid systems, it's almost always the Helmholtz energy. So if you look at a molecular simulations paper or advanced statistical, I always struggle with that word, phase equilibrium studies, it's almost always Helmholtz. Okay, so if we do the energy balance for this system, we have U at state 2 is equal to U at state 1 plus Q plus W. So this is basically just a rearranged form of what we did as the integral form of the expression. Or we could just also write this as delta U is equal to Q plus W. Let's do an entropy balance as well. In this case, we'll just jump ahead again and say that delta S is equal to Q over T plus S gen, in which case S gen is the total amount of entropy generated, not the rate of entropy generation. So for starters, we're going to assume that there is no entropy being generated, just to make things a little bit easier on us. This is a reversible process, which means it happens infinitesimally slow. So what we'll do now is we'll substitute in the entropy equation into the into the energy equation. So in this case here, we have that delta S is equal to Q over T, or Q is equal to T times delta S, which we can then substitute directly into there. And we will get that delta U is equal to W plus T delta S. Hopefully things should start to look somewhat familiar now, and that the work we could rearrange is equal to delta U minus T delta S. And what do we define this as?
Helmholtz energy.
This is the Helmholtz energy, defined as delta A, the Helmholtz energy. Oftentimes we'll say that this is the reversible work that comes out of a NVT system, closed, isothermal, and constant volume system. But conveniently, as it turns out, the Helmholtz energy is also very valuable for phase equilibrium. So in general, we won't use Helmholtz or Gibbs at all talking about work, but that's sort of originally how it was defined. We mostly care about it for phase equilibrium, because that's where it comes into much more handy. For a real system, the work out of the system is equal to the reversible work plus Ts gen. And in this case, how we defined our system, we had that negative work is out of the system. So if we have entropy in the system being generated, that means you have less negative work, which means that you're not getting as much useful work out of it. It's a little upside down logic, but the math checks out, right? So if Ts gen, right, T has to be greater than 0, entropy generated has to be greater than 0, which means that it brings the actual work output closer to 0 because we're looking for negative work. Okay. Yes?
So what is this work if the volume can't expand? What?
It's sort of a magic impeller or shaft work. So it's kind of like there could be, so in this particular system right here, there could be all sorts of widgets and gadgets going on the inside. But we're just drawing an arbitrary box around some sort of a magic process. Just like the Carnot cycle derivation. We're saying, oh, the Carnot cycle is this circle trapped in between a hot reservoir and a cold reservoir. But we don't necessarily know what is the magic mechanics going on between there. So this could be an impeller, turbine, all types of things like that.
Chemical reaction?
I don't think well, a chemical reaction could be a part of it, but you would still need to convert that somehow to mechanical work to get the work out.
Okay.
Yeah. It's So like you had a reaction that expanded a gas like an explosion, that could count potentially, I would think, yes. Okay, so now let's move on to the Gibbs. In this case here, the Gibbs ensemble is what we call the NPT. So it's going to be isothermal, closed. Sorry, the closed corresponds to the N, meaning constant number of material in the system. Isothermal corresponds to the T, and I'm writing this out in this most confusing way possible. And then isobaric, which corresponds to the constant P. All right, so NPT means you're holding the number of moles constant, you're holding the pressure constant, and you're holding the temperature constant. In the case of Helmholtz, NVT, same thing, but switch pressure for volume. We'll draw out our system. In this case here, the volume is not constant, but pressure is constant. Temperature is constant. We can have a Q term going in, and we can have a work term going in. And in this case, there are potentially two forms of work, right? We have, this is the shaft work, sort of the magic work that we talked about in the last example, and we also have PV work. Now, who can recall how would we define PV work? How would we mathematically characterize it? This is something we'll often see in a piston cylinder device.
So I just remember you just multiply the change in volume by pressure.
Bingo. In this case, it's actually minus P delta V. Right? Because as the volume grows, you're sucking energy away from the system, or vice versa. Okay, so now I'll give it to you guys to derive, most of you already know what the Gibbs free energy looks like, but walk through the process of deriving the Gibbs free energy. It is already there, but I bet most of you already knew what Gibbs was defined as anyway. But, so do the energy balance, then do the entropy balance, substitute them together, and we should get out the Gibbs free energy equation. So I'll give you a couple minutes to do that, and then we'll do it really quickly on the board. Okay, so let's go through it real quick. Energy balance. We have delta U, right? So in this case, we're just keeping track of all of the sources of energy in and out of the system, and then that delta U is the imbalance between all of those. So delta U is going to be, we have potentially Q coming into the system, we have shaft work potentially coming into the system, and minus P delta V coming into the system, or in this case, expansion work. delta U plus P delta V is defined as delta H equals Q plus W. W is equal to delta H minus Q. We'll do our entropy balance. Same as the last one, delta S is equal to Q over T plus S gen. We'll say that's equal to 0. Q is equal to T times delta S. Substitute them together, and we get WS is equal to delta H minus T delta S. And we define that as the Gibbs free energy of the system. But again, Gibbs is, for our concern, way more important for phase equilibrium, because delta G across the phase transition is 0. Okay. So now we're going to use the entropy balance again in a different way to talk about entropy generation. So our system that we're going to define, we're going to have side A, we're going to have side B. This is going to be completely isolated. Okay, so across this boundary, 0, it's going to be a closed system. And the only thing that can happen in this system is that Q could transfer from one side to the other. And let's see, how do I have this defined? DAS. I think I have Q defined positive as going in this direction here. So this membrane in between A and B only allows for thermal conductivity. No mass, nothing, just heat is exchanged between the two of them. So we're going to use this system to try and understand how entropy is generated. So we're going to throw in a little bit extra physics that we know sort of now. We're going to say that Q is equal to is proportional to TA minus TB, or that Q is equal to H times TA minus TB. Right? This is kind of like a thermal conductivity or heat transfer coefficient, whatever you will. So if we look at our entropy balances, if we do an S balance on just system A, we have dSA dt is equal to Q dot over T plus S gen. So what we're actually going to say is that the entropy on the A side, there's no entropy generated. Everything's perfectly homogeneous and nice. And then we'll say, based on how we defined the Q, we will say that this is equal to minus H TA over minus TB over TA. We'll do the same thing for the B side. dSB dt is equal to H times TA minus TB over TB. Notice that the minus sign is gone because the heat is going from one into the other. Now, we don't actually have to know which is bigger, TA or TB. The math will all work itself out. If we drew the arrow incorrectly, it'll all correct for itself. So now, next step is we'll do a total entropy balance. ds dt, so the total change in entropy of the system, is going to be equal to q dot over t plus s gen. Now we've said that the system is completely isolated, so there is no heat transfer in and out of the total system. Everything's contained within. Only stuff is happening between chambers A and B. But entropy is extensive and additive. So we add up the contributions of the total entropy from the subsystems. So in this case, it's going to be dSA dt plus dSB dt. So if we substitute them together, we get that, let's see, I'll write this differently here. So we can do a little bit of math rearranging here. I'll skip over that. So the conclusion that we reach here is that entropy is generated in this system when you have a temperature difference between chamber A and chamber B. And the larger the temperature difference that you have between those two chambers, the greater the rate of entropy generation. So this holds true. In this example, we did it just based on two reservoirs in thermal contact. But this holds true for any type of gradient. Entropy is generated when basically we have an irreversible process. Right? When heat goes from hot to cold, it'll never go back from cold to hot again, basically because it violates the second law of thermodynamics. So any process that has entropy being generated is one where there is a gradient. But basically, we have to have a gradient for anything to happen. For fluid to flow, there needs to be a pressure gradient. For mass to diffuse, you need a concentration gradient. For heat to diffuse, you need a temperature gradient. So in this particular case here, this shows us that we can never actually do a truly reversible process unless we can find a way to do the reversible process when there's no gradients, which means it takes an infinite amount of time to do anything reversibly. So it merely is just an arbitrary construct that makes our math easier to work with. But ultimately, the reason why reversible processes are so useful is because it allows us to basically generate kind of like, enthalpy tables and entropy tables, because we do want to magically figure out how to heat up water from 1 atmosphere and 20 degrees C to 500 degrees C in 10 atmospheres, right? We want to know how much energy that process takes, and if we're doing the calculations, why not magically choose some sort of a reversible system to do it in? So the math of reversible systems is very convenient, but in reality, it's never going to happen. So if I were to heat up sort of a pot of water, right, would it be better to use a very hot flame or a slightly less hot flame if I wanted to get maximum energy efficiency out?
Small flame and slowly increase.
Exactly. That's the most efficient use of energy, but obviously it takes a lot more time to do so. So if you've got a larger temperature difference between two bodies, you're effectively losing energy. Now the notion behind that is, let's say, and there's a homework problem on this, so I'm giving away a little bit of this, the fun of the problem. If I have a heat exchanger where this is a cold side, and then we have a hot side, and of course, this is not how you would actually build a heat exchanger. There would be much more interconnected. right? But in this case here, the larger the temperature difference between the hot side and the cold side, the greater the rate of entropy generation. Because effectively what you're doing is all of the gunk that's in this hot side heat exchanger, that has a lot of useful energy. So if you were to take this energy and sort of run it through a Carnot cycle, you could be squeezing work out of it. But instead, if you're just taking really hot fluid and putting it in contact with really cold fluid, you're effectively taking all of that useful energy that could be converted through through an engine into work. You're basically throwing that away and just converting it directly to heat on the colder reservoir. Yes?
I mean, what if you're doing a design in a plant, you use a hot, like you had a hot thing, and you use it as a preheating cycle before you did your reaction or did your heating?
So this is an idealized situation here. So in a real process, there'll be a lot of other factors in terms of, is it worth the money to pipe it over there? But in general, it's better to use a smaller gradient to get the most useful energy out of the system. But it all comes down to whether or not it's even worth your time. But from a fundamental thermodynamics perspective, large gradients means lots of wasted energy. So you wouldn't want to take, superheated steam and put it in contact with ice water. First of all, it doesn't make a lot of sense too, because why would you do that anyway? But in general, that's how entropy is generated. So pressure gradients, concentration gradients, temperature gradients, any gradient always generates entropy.
Also, processed water is very expensive in terms of coolant.
Yeah. But again, there's lots of other considerations. This is sort of a fantasiful, just in general. And this is one of the few circumstances where you can actually calculate the entropy generation rate. In general, it's extremely difficult to do so. So more often than not, we will not consider entropy generation. Because it's sort of, you can only calculate it in very specialized circumstances. Yes, question?
So does that mean that inherently countercurrent heat exchangers are more efficient because
Oh, yeah. That's a good perspective. That might be the case. It might be sort of a thermodynamic underpinning of practicality. And I think from a heat transfer's perspective, countercurrent is better because I think you get more efficient use out of the surface area because so actually, I don't know. I'm thinking about it now. The reason why countercurrent is better is because you have you maintain the biggest gradient throughout. So maybe actually it is counterintuitive. Maybe it makes more entropy as a result of it because you're transferring heat better. Because in the co-current case, you have the maximum gradient here and the minimum gradient there. But in the countercurrent flow, it's the same gradient throughout, or close as you can get.
Whenever you do the math, you have a more efficient heat transfer most of the time with the countercurrent.
So with the countercurrent, yes, you get better heat transfer. But in this case, the idea is not to sort of maintain the most amount of useful work out of the system. The idea is to minimize the materials used to construct the heat exchanger. So I guess in that case, it's way more important to minimize the amount of materials in the heat exchanger. Yeah, good perspective. Okay, so we've got about 10 more minutes, a little bit more. So we're going to talk about deriving a combined first and second law expression that is going to be the starting point for most all of the derivations that we're going to do to grow, basically rederive all of thermodynamics. Right now we've tinkered with the first law, we've tinkered with the second law, but now we're going to generalize it to have one overarching expression that we can then simplify down based on the needs and circumstances. So we're going to call this, I'll just call it this the combined first and second law is really what I like to think of it as. So I don't think we'll have time to go over that sheet that I handed out. We'll talk about that on Wednesday. That's the next step in the derivations. Okay, so we're going to construct an open isothermal isobaric system. So temperature is constant, pressure is constant. We're going to have Q, W, and mass flowing into the system. And then we'll also have the PV expansion that comes along with it as well. So we'll start off with the mass balance. The rate of change in mass of the system as a function of time is just going to be equal to the amount of mass flowing into the system. Right? And if we were to solve this and integrate this expression, right, we would need an initial condition of how much mass there was originally in the system. Energy balance. We're just going to keep track of all the sources of energy in and out of the system. So we have energy entering the system in the form of the chemical bonds and molecular motion of the mass flowing in. But again, that's based on what we know now. But back in 1800s, it wouldn't necessarily been the case. They wouldn't have known how the energy was stored in the system. We have heat energy coming in. We potentially have shaft work, which is an impeller or a turbine or something like that. And we also have minus P dV dt, which is the PV expansion work in the system. Again, negative because as the system grows, you lose energy because it has to push back the atmosphere. Now we'll do a second law, ds dt. Right, the mass that's flowing into the system is bringing with it its own entropy, just like it's bringing in internal energy. Okay, so now what we're going to do is we're going to just substitute in the mass balance into the first and second laws. So we get du dt is equal to h hat dm dt. For simplicity's sake, we're just going to drop off these dt's and just note that whatever we're deriving is over some differential element in time. Okay. Everyone good? So if we rearrange the second law, we can get that Q is equal to T. Hold on, let's see, what did I do here? Oh, okay, I see what I did. Okay. TDS minus TS hat DM plus Q plus TS gen. The TDS comes from the left-hand side of the equation that we were writing on. Now if we sub this Q into the energy balance, du is equal to h hat dm minus T ds minus Ts dm. A lot going on right now. We'll simplify it down in just a second. We're going to say we're not doing any work in the system, and we're going to assume it's reversible. And so from there, we can simplify this down to du is equal to T ds minus P dV plus and we can further simplify this to du is equal to T ds minus P dV plus G dm. And we have the combined first and second law. So as was mentioned on the first day of class, basically, the goal of thermodynamics is to relate between basically the three fundamental variables of the universe: energy, entropy, and volume. And in this case, it's an open system. Obviously, mass is an important part of that as well. Right? But recall, for a closed system, right, dm would be equal to 0. And we would just have du is equal to Tds minus Pdv. So this is an expression that explicitly relates between those variables. Now, as sort of a preview of what we're going to be talking about on Wednesday, through general calculus, we can write du is equal to du ds times by ds plus du dv, right? So basically, if you're trying to calculate how much a total function changes, in this case here, right, we want to know what is the total amount of change in the internal energy of the system. But there's lots of things that can change it. So you're adding up the incremental change with respect to entropy, the incremental change with respect to volume. So you can kind of think of it as like, how much does your total amount in your bank account change? Well, you've got some change going on because you're spending more money. You've got some change going on because you're making more money. Right? It's the same notion there. And so to keep up what is the rate of change in your bank account, you'd have to calculate, well, what is the rate of change in my spending? What is the rate of change in my making? So mathematically, that's how we write this in terms of calculus. Right? This is d. The big D here is the total differential. The partial differentials are with respect to individual variables. But if we take just a general calculus expansion, in this case here, du expanded with respect to entropy and volume, S and V, right? We know from the Gibbs phase rule that we only need to expand any thermodynamic function out by 2. If it's an open system, you need to expand it out by 3, right? Because 3 variables completely define the universe. So if you're expanding internal energy, there's only 2 other variables that you have to expand. Now, as we'll soon develop, if we're expanding out enthalpy, you still may have to expand out 2, right? Because you're adding up all of these just arbitrary functions. So what this allows us to do is it allows us to relate between different functions here. Right? And these are the same definitions that we talked about on day 1, whereas the temperature is equal to du ds. In this case, for convenience, we often write down at constant v, but it's a partial derivative, so everything's constant no matter what. Right? But for convenience in thermodynamics, and as a reminder of the assumptions of the system that you're working with, we typically will write down what variables are held constant. But you should know that in a partial, everything is held constant. This is only a convenience that's common in thermo. And that minus P is equal to du dV at constant S. So these are the same functions that we defined on day 1, talking about how temperature and pressure were derived from the base units of basically thermodynamics, U, V, and S. And if you look on your sheet, there's a section called thermodynamic identities. These are 2 of them. And we can also use the same sort of workings out to derive Maxwell expressions, which we'll talk about on Wednesday. But the combined first and second law is the starting point for basically the entire foundation of what we're going to do in the class. It'll be the starting equation that we will manipulate, substitute, perturb, to develop Gibbs, fugacity, everything. Okay. So we're out of time, unfortunately. Any questions? Please do take a look at the homework. I don't think any particular problem should be stressfully hard, but it's a lot of stuff that you'll have to rely a little bit on sort of practice from old thermodynamics classes. So any questions or issues you have, bring them up in class so we can kind of go over them if it's all confusing. All right. Have a good week.